Welcome to our presentation on impulse response analysis, a cornerstone technique in modern time series econometrics. Our goal today is to unlock the concept of dynamic causal effects, moving beyond simple static correlations to understand how economic systems evolve over time. We will cover the theoretical underpinnings and then demonstrate a practical application using EViews. For instance, instead of just knowing that interest rates and inflation are correlated, we want to know how a sudden, unexpected 1% increase in the interest rate today will affect inflation over the next 2 years. The definition on the right, from the EViews User Guide, states, impulse response analysis traces the impact of a shock to a single variable on the current and future values of all endogenous variables. So, what is the fundamental problem that impulse response analysis helps us solve? Let's explore the shift from a static to a dynamic perspective. In many economic analyses, we often start by looking at static correlations. This is like taking a single photograph of the economy. It tells us what variables move together at a specific point in time, but it doesn't reveal the story of how changes unfold over time. The fundamental problem we aim to address with impulse response analysis is to move beyond this static snapshot to a dynamic understanding of causation. On the left, we see a shock, for instance, an unexpected oil price spike, hitting the economy, represented by a system of gears. The key concept here is dynamic causation. Our goal is to understand not just if two things are correlated, but how the entire economic system reacts over time to such a surprise innovation or external shock. We want to see the movie of the economy, tracing the effects of this shock on crucial variables like GDP, inflation, and wages at different time horizons, such as 1 period later, T+1, 2 periods later, T+2, or even 10 periods later, T+10. This dynamic perspective is crucial for understanding economic policy and forecasting. This slide outlines the systematic approach to choosing the correct econometric model for impulse response analysis based on the statistical properties of your time series data. The first critical step is always to analyze your data properties, specifically checking for stationarity. If your data is stationary I0, meaning it is mean reverting, then the appropriate model is a standard VAR, vector autoregression. From this, you would then derive the orthogonalized IRF, impulse response function. However, if your data is non-stationary I1, meaning it becomes stationary after first differencing, you need to conduct a cointegration test. If the variables are cointegrated, indicating a long-run equilibrium relationship, you should use a VECM, vector error correction model. If they are not cointegrated, you would typically estimate a VAR indifferences. Regardless of the path taken, the final crucial step is to apply an identification strategy, which could be Cholesky, generalized, or structural, to ensure the shocks are economically meaningful. The quick check on the right summarizes these points. If your data is stationary, use a standard VAR. If it's non-stationary but cointegrated, use a VECM. And if you have an unknown order for identification, consider using generalized impulses as an alternative to Cholesky. This slide introduces the Wold representation theorem, a fundamental mathematical principle that underpins impulse response analysis. It states that any stationary time series, denoted here as YT, can be expressed as a linear combination of current and past error terms, often referred to as innovations or shocks. In the equation shown, YT is our response variable of interest. Mu is its mean, and epsilon t represents the innovation, shock, surprise, at time t. The terms psi1 epsilon t minus 1 and psi2 epsilon t minus 2 are examples of weighted past shocks, where psi sub s are the impulse response coefficients. In simpler terms, these coefficients are key to understanding the dynamic effects of a shock. Psi sub 0 represents the immediate impulse or impulse of a shock. Psi sub s measures the ripple effect, which is the impact s periods later. Crucially, the coefficient psi sub s quantifies the marginal effect of a shock that occurred at time t on the value of the variable at a future time t plus s. Finally, the cumulative sum psi sub s represents the overall long-run effect of the shock. Identification is the process of imposing economic theory to separate correlated error terms into structurally meaningful, uncorrelated shocks. The most common method is the Cholesky decomposition. This method assumes a recursive, or causal, ordering among the variables. It transforms the correlated errors, epsilon t, into a set of uncorrelated shocks, ut, using a lower triangular matrix P. The crucial rule here is that ordering matters. The variable placed first in the ordering is considered the most exogenous. It affects all other variables contemporaneously, but is not affected by them within the same period. Conversely, the last variable in the ordering is the most endogenous. It is affected by all other variables contemporaneously. This decomposition forces a specific causal ordering to separate correlated errors effectively. To ensure our impulse response functions are valid and reliable, we need to consider two key assumptions. First, stability, meaning the effects of a shock must eventually die out and the system returns to equilibrium. If the system is unstable, the impulse responses will explode and be meaningless. Second, white noise residuals, which means the model's errors should be uncorrelated over time. If they are correlated, it suggests our model is misspecified. The graph illustrates a typical impulse response, showing the solid line as the point estimate and the shaded bands as the 95% confidence interval, which helps us gauge the statistical significance of the response at each point in time. As a crucial diagnostic tip for stability, always check the AR roots of your VAR polynomial before running an IRF. If any root is near 1, the system is unstable, and the IRF will not converge or it will explode, rendering your results unreliable. To begin in EViews, you first need to have a VAR object estimated and open. The standard navigation path is to go to the VAR object window, click on View, and then select Impulse Response from the drop-down menu. A much faster way is to use the command line. Simply type the name of your VAR object, followed by a period and the word impulse, then press Enter. If you have estimated a VAR and saved it with the name var01, you can simply type var01.impulse in the EViews command window to directly open the impulse response dialog box. Once you've opened the impulse response dialog, you'll be presented with several options for how to display the results. Let's look at those settings next. This slide focuses on the display settings within EViews for impulse responses. From the Impulse Responses window, navigating to the Display tab allows you to configure how your results are presented. We typically choose multiple graphs for a clear, separate visualization of each impulse response. You can also specify the number of periods you want to analyze the shock's effect over. A crucial pro tip highlighted on the slide is to check accumulated responses if your underlying data is differenced. This is vital because it converts the interpretation from an effect on the growth rate to an effect on the level of the variable. For example, it lets you see the impact on the level of GDP from a shock to the growth of GDP, providing a more intuitive economic interpretation. On this slide, we delve into the Impulse Definition tab within EViews. This is where you select the decomposition method for your impulse responses. The residual, one standard deviation, method, often highlighted as the recommended standard, implements the Cholesky decomposition. You should select this if you have a clear theoretical ordering for your variables. Alternatively, if you lack a strong theoretical basis for ordering, you can choose generalized impulses, which are invariant to ordering but might be harder to interpret structurally. For advanced users with specific structural restrictions, user-specified methods are available. Crucially, if you opt for a Cholesky decomposition, you must explicitly define the causal chain of your variables in the Cholesky ordering box, remembering that the order of variables matter for interpretation. For our case study, we're analyzing the effects of shocks using three key macroeconomic variables: the federal funds rate, or FF rate, the GDP gap, and inflation. The first step involves preparing our data and estimating a vector autoregression, or VAR, model, which is represented by the tables you see on the slide. A critical aspect of our analysis, especially for interpreting impulse responses, is defining the causal ordering of these variables for the Cholesky decomposition. This ordering is not arbitrary. It's based on economic theory regarding how quickly these variables respond to new information or shocks. We establish the ordering logic as follows. First, GDP gap is placed at the top. This is because we consider the real economy to be the slowest to react to economic shocks. Second, inflation is introduced. Inflation typically reacts more quickly than the GDP gap, but still with some lag. Finally, the FF rate is positioned last. This represents the policy variable, assumed to be the fastest reacting and capable of responding contemporaneously to changes in the GDP gap and inflation within the same period. This theoretical ordering is crucial for correctly identifying and interpreting the structural shocks in our model.
Our research question is, how does a tightening of monetary policy affect the real economy? To answer this, we define the impulse as the variable that receives the shock. In this case, it's FF rate, representing the monetary policy instrument. The responses are the variables we want to observe the effect on. Here, we are interested in the real economy, so we list GDP gap and inflation. We will trace the effect over 12 periods, quarters, using the Cholesky decomposition method we previously defined. By setting FF rate as the impulse and GDP gap as a response, we are simulating an unexpected one standard deviation increase in the policy interest rate and then tracking its effect on the output gap over the next 3 years. After clicking OK, EViews generates the impulse response graphs. Now comes the most important part, reading and interpreting the output. The output is a series of graphs. Each graph shows the response of one variable to a shock in another. The solid line in the middle is the point estimate, which is our best guess of the response over time. The dashed lines on either side represent the confidence interval, typically at the 95% level. This gives us a range of plausible values for the response. The horizontal line at 0 represents the null hypothesis of no effect. The key interpretation rule is, if the confidence interval bands encompass the 0 line at a particular time horizon, the effect is considered statistically insignificant at that point. Looking at the graph for the response of GV to G, if at period 5 the lower confidence band is at negative 0.2 and the upper band is at positive 0.3, the interval contains 0. Therefore, we cannot conclude that the shock has a statistically significant effect on GV in period 5. While this statistical interpretation is crucial, the ultimate goal is to translate these graphs into a compelling economic story. A one standard deviation shock to interest rates, tightening, leads to a significant decline in the output gap starting in Q2, peaking in Q4. A key weakness of the Cholesky decomposition is its dependence on the specified variable ordering. A different ordering can sometimes produce different results. Therefore, a crucial best practice is to perform a robustness check. This involves re-estimating the impulse responses with a different, plausible ordering and comparing the results. In our example, we compare ordering A, GDP, inflation, interest rate, with ordering B, interest rate, inflation, GDP. If the essential economic story, the shape, sign, and significance of the response remains the same under different orderings, we can say our result is robust. If the results change dramatically, it suggests our identification is weak and we should be cautious in our conclusions. As shown on the slide, the response of GDP to an interest rate shock looks very similar in both ordering A and ordering B. This gives us much greater confidence that our finding of a delayed, temporary economic contraction is a genuine feature of the data, not just an artifact of our initial assumption. Here are some handy EViews commands for running impulse response functions more efficiently. The most basic command is simply var01.impulse to generate the default impulse responses. You can add options in parentheses for custom specifications. For example, var01.impulse m, se equals a specifies multiple graphs mode indicated by m and requests analytic standard errors using se equals a. To specify a Cholesky decomposition with a custom ordering directly from the command line, you use imp equals chol to specify Cholesky decomposition, and the order option, followed by your variable names in quotes, such as order equals GDP gap, inflation, FF rate. Finally, a very useful command is freeze. This command captures the current output, such as a set of impulse response graphs, and saves it as a permanent graph object in your work file. You would use freeze mygraph var01.impulse, where mygraph is the name you assign to the saved graph object. This allows you to easily edit and export the graphs later. To summarize our discussion on impulse response analysis, there are 4 key steps. First, always ensure your data exhibits stationarity and the VAR system is stable. Second, choose an appropriate identification strategy. Cholesky decomposition is a standard choice. Third, check the statistical significance of your impulse responses, typically using confidence bands. And fourth, the ultimate goal is to interpret the timing, magnitude, and persistence of the effects to tell a clear economic story. For further reading, we recommend Sims, 1980, on macroeconomics and reality, Lutkipol, 2005, for a new introduction to multiple time series analysis, and the EViews 13 User Guide I for econometrics. You can also find additional resources, including datasets and tutorials, on www.vietlod.com and youtube.com/user/vietlod. This slide serves